this section of the course, we're going to begin to put together some of the things that we've discussed in several previous lectures. So we're actually going to look now at what is involved in the instrumentation and the placement of electrodes to actually make a measurement of a biopotential. The overwhelming number of slides in Chapter 6 in your textbook concern the ECG, which is your textbook author's area of expertise, he and his collaborators. So there will be a lengthy discussion of the ECG, the probe placement, the instrumentation, some of the considerations, as well as in a later lecture, the interaction of the measurement with the environment. So many of the things that we've discussed up to this point, like amplifier design, sensor design, electrode design, and origin of biopotentials, will sort of all come together in this chapter where we discuss making an actual measurement. So the first thing that we'll talk about is overall in general, when you design a biopotential amplifier, what are some of the characteristics that you look for in one that would be appropriate? The first characteristic is that the amplifiers must have a high input impedance. This reduces the effects of loading on the system or the circuit, which would distort the signal. Typically, you want 10 megohms of input impedance in a modern biopotential amplifier system. So that high input impedance means that then whatever the measurement system adds as a quote-unquote additional load won't pull current from the measurement and impede or interact with the measurement itself. Secondly, you will have to have some isolation and protection circuitry to protect the person from electric shock. So you don't want an amplifier system that's plugged into a wall circuit without some kind of isolation. You don't want amplifiers that have large external power supplies that could somehow interact with the body. So the isolation and protection circuitry is very important. You should also have an amplifier that has a low output impedance compared to the input impedance and that can provide adequate power to then drive the load of the measurement system. It's important that the amplifier operates in the frequency spectrum of the signal being measured. You don't necessarily want a broadband amplifier. You would like for the amplifier to be optimized to work in the frequency region of what you're measuring. Typically, biopotential amplifiers are differential amplifiers, and they would be designed to have a high common mode rejection ratio. So that's another common characteristic or feature. And then finally, from a practical point of view, you have to realize that these instruments are not used by people with PhDs in engineering. They're used by clinicians. And the people who work on these systems are generally not people who have PhDs in engineering, but people who are trained as technicians in the field. When equipment breaks, there is usually a fairly high demand that it be repaired as soon as possible or calibrated as soon as possible. So calibration and repair needs to be where it can be done quickly, where it can be done in the field. You don't want to have to send your ECG machine back to the manufacturer for repairs. It needs to be something that a well-trained technician can do, and calibration, preferably something that the ECG tech themselves can do. So ECG amplifiers measure the heartbeat signal, and the heart signal can be modeled as a dipole field, where the location and the orientation of electrodes are important due to the physical orientation of the field. So remember, biopotentials originate from these cell potentials, and that creates an electric field distribution in the body. And if we have an electric field anywhere, and we place two sensors along the field lines, we will detect a potential difference because electric field lines basically represent directed differences in potential. So if we go across electric field lines, we would not expect to see a potential difference, but if we go parallel to electric field lines, we would. So for this reason, the location and the orientation of electrodes are extremely important because the electric field has a particular orientation. So here is a little schematic of the human body showing the cardiac vector M, which is just a generalized electric field that exists due to the electric field within the heart. And then remember, this is going to oscillate as the electric field waves move throughout the chambers of the heart. But we can sort of represent this as a steady state dipole moment vector with a given direction M that originates from this electric field due to activities within the heart and separation of charge within the body. So this is and this is basically, this vector diagram is frozen at the point when that R wave is maximal. So as I said, both the magnitude and the direction of this vector can change. It would flip direction and increase and decrease in magnitude depending on where you are on the waveform of the heartbeat. So obviously, this is an electric field direction. If you place electrodes along this line, you'll measure a potential difference. If you place electrodes parallel to this line, you will not. These circles here are equipotential surfaces. So if you measure along a particular line or circle, you won't measure potential difference, but across them you will. So electric equipotential surfaces are perpendicular to electric field lines. So a pair or a set of electrodes is referred to as a lead, and as we discussed before, the orientation of the pair of electrodes is called the lead vector. So let's look at a figure that describes that. Here's our cardiac vector. Here's lead A2, lead vector A2, and lead vector A1. These would be obviously pairs of leads. And as you can see, A1 has some component in the direction of the electric field, and so you would measure a voltage there equal to the magnitude of the field vector times the cosine of the angle between the lead vector orientation, and the electric field vector orientation. Note that lead vector pair A2 is perpendicular, and there is no component of the cardiac vector in the direction of A2, so you would not detect a voltage with that lead pair. So in clinical ECG, you have to use more than one lead and more than one lead pair. You have to record that to really fully describe the heart's electrical activity. In practice, you would take several leads in the frontal plane, which is the plane that's parallel to the ground when you lie on your back, as well as the transverse plane, which is the plane of your body that's parallel to the ground when you stand up. So three basic leads. So this first is referred to as the frontal plane, and we'll talk about that in the next several slides. Three basic leads make up the frontal plane ECG, and they're derived from various permutations of pairs of electrodes. When one electrode is placed on the right arm, one is placed on the left arm, and one is placed on the left leg. And then typically you will also have a right leg electrode that is used to represent a ground or to connect to some external circuit that serves some purpose, usually mitigating outside noise. So this results in something that is referred to as Einthoven's triangle. And so you get lead vector 1, which is left arm to right arm, lead vector 2, which is left leg to right arm, and lead 3, which is left leg to left arm. This forms roughly an equilateral triangle. It's known as Einthoven's triangle, and that then is in the frontal plane of the body. So let's look at the figure. So here's the figure, and here's Einthoven's triangle. So let's suppose we had this cardiac vector here, and if we basically the components of the cardiac vector can be determined. When you put the vector within the triangle, you can resolve it into its components. And so in this case, you can see that our V3 component would obviously be 0, but we would get a component in V1 and V2. So these lead pairs are measuring the components of this vector. So not only could we determine what the magnitude of the vector is, but we could also determine its direction by looking at the components along the different lead vector directions. The cardiologist will use a standard notation referring to the direction for lead 1 as 0 degrees, lead 2 as 60 degrees, and lead 3 is 120 degrees. So you can see if we took the tail of this vector and we slid it along here, it would form a 120 degree angle with lead 1. And obviously they're measuring this in the downward direction, which is different from what we would do if we were doing like a vector analysis of an electric field or a vector analysis of a circuit. We tend to measure in the clockwise direction. They're in the counterclockwise direction. They're measuring clockwise. So a negative angle, from what we as electrical engineers would interpret, is a positive angle as described by cardiologists. And then you can also see that if you were to do a vector sum, that eventually you would get back to where you started. And so the vector sum is basically 0. If we count lead vector 1 as positive direction, so we go from tail to head, then notice here we're going from head to tail. So the 2 in this equation is listed as negative, and this would be a vector sum. So in addition to these leads, there are actually 3 additional leads in the frontal plane, as well as a group of leads in the transverse plane that are routinely used in taking a clinical ECG. And these are based on signals that are obtained from more than one pair of electrodes. They're often referred to as unipolar leads because they consist of the potential appearing on one electrode taken with respect to an equivalent reference electrode. And this equivalent reference electrode is basically the average of signals seen at 2 or more electrodes. So it's convenient to talk about Wilson's central terminal. Wilson's central terminal, basically the 3 limb electrodes that we've talked about are connected through equal valued resistors to a common node. And the voltage at this node is Wilson's central terminal, and it's the averages of the voltage at each electrode. So let's look at a figure. So first of all, here is just a slightly different illustration of lead 1, lead 2, and lead 3. And what we're interested in are these additional potentials VR, VL, and VF. And the reason is that this gives us some, if we can get these potentials, it gives us some indication, once again, of components in these directions, which can give the cardiologist an indication of if there is a malfunction in the heart, exactly what part of the heart is impacted. Clearly, this is not as good as imaging studies, but certainly this is a 5-minute test, and so that's the advantage of being able to make some interpretation from the ECG to give guidance on what kind of diagnostic test to do next. So here is a block diagram that indicates this concept of Wilson's central terminal, that you would have basically 3 equivalent resistors, and they would all connect here to what is referred to as Wilson's central terminal. So it is a circuit model of the body system and the creation of this terminal to give you a reference terminal. So now to find these, what we call augmented limb leads, these additional electrode connections, we can use this circuit model. So for example, if this were not open circuited and this were R, this would be Wilson's central terminal. But if we now open circuit here and measure this voltage, then we're measuring what is referred to as AVR, augmented on the right side. This is augmented on the left side, and then this is augmented at the foot. And so you can see how that's modeled from a circuit's perspective. Now, if we were to go back to the vector diagram of the limb electrodes, we would be able to see here is 1, here is 2, and here is 3. If we were to go back to that additional triangle, let me go ahead and go back there and show you that figure one more time. So here's that figure, and that sort of virtual Wilson central terminal would be here in the middle. And so here is AVR, here's AVL, and here's AVF, and you notice the directions are different. And if we let this be 0, then AVL would be minus 30, AVR would be minus 150, and AVF would be 90. So now we can go back to that other figure, and here that is represented. Now, what this really allows you to do then is this allows you to get additional component vectors of the ECG wave, which just gives you more information about the magnitude of that dipole field in different directions, and thus allows the cardiologist to know, is there some issue with a portion of the heart that is impacting the direction of that dipole field, or is it normal? These are just some simplified circuit diagrams of what that might look like if we were to model it as a circuit. I'm not particularly wanting you to necessarily have this circuit model memorized, because it's just basically it's just a reproduction of what was shown on the previous figure, but not quite as clear. So in addition to that, frontal plane, we can also get an ECG in the transverse plane, and this uses a set of 6 chest leads that are referred to as precordial electrodes. And if you've ever had an EKG, you've probably had probes placed here, or an ECG. And so basically there are 6 leads, they run around here, and this is in addition to the left arm, left leg, and probably right leg. What this allows you to do is, if you look here at a top view of the body, this would be the angular placement of these leads from the perspective of looking top down. So going from right to left, so if this V6 is defined as 0 degrees, then you get this distribution. Notice that this is not quite as good as the frontal, because you don't get anything in these 2 quadrants. You only get a little bit, only 1 lead in this quadrant. Most of it's distributed in this quadrant here, but for most purposes, that's adequate. So once we have our lead placement, what exactly happens to the connections that come from these leads? So this is just a block diagram that shows one example of the electrocardiograph. You have your sensing electrodes, and then typically you have some circuitry that determines, is there something wrong with one of your electrode leads? And that's important because when looking at the ECG, you sometimes will have a lead that comes loose. This was particularly common. I know one of my babies was born premature, and there was an alarm hooked up in case the heart rate failed or became irregular. It went off all the time because the leads became loose. So having a loose lead detector is important, and typically having some kind of display that says this is only a loose lead detector so that people know not to freak out and just to tighten the lead is also important. You then have your protection circuitry that basically prevents the circuitry that's going to make the measurement and condition the signal from coming back to the body. There is a lead selector, and typically you will have parallel circuitry that does like a simultaneous recording from different leads. If you're an electrical engineer and have that background, you know that at some time you need to do your A to D conversion. And a lot of times that is actually done at or near this stage, as opposed to how it's shown in the figure. And then your sampling is done across. It's multiplexed across different channels. So from the lead selector, then you go into the preamplifier, which will do some filtering as well as restore any baseline to zero. Usually there is some kind of auto calibration that's done just prior to the preamplifier stage. So you would have some kind of a microcomputer system that comes in and does some sort of auto calibration. The preamplifier then goes into the isolation circuit. There's a there's an external circuit that sometimes exists called the driven right leg circuit. We'll discuss that in a bit. It basically exists to help mitigate external noise and external factors. From the isolation circuit, then you go into a driver amplifier, A to D conversion, and into memory, as well as into some kind of recorder. Now, let me say that a lot of this, some of this is in research instrumentation, now obsolete. Now instrumentation tends to do the A to D conversion immediately, just past the sensing electrode phase, so that all of the amplification and the signal multiplexing and everything else is done in the digital domain. That is beginning to filter into clinical systems. Clinical systems still tend to use a lot of analog, especially older and less expensive clinical systems. But now there are handheld digital systems that basically incorporate all of this into a single handheld device that has multiple leads. And I have one of these in my lab. I wouldn't recommend it for clinical use, but it's available for training, and it is, once the leads enter the amplifier, it is a fully digital system. Here are some just performance requirements, and you can see this is part of the problem. This is listed in 1991. This textbook was published in the early 2000s. The change in medical instrumentation to fully digital systems, the improvement in computer capabilities has been huge. However, a lot of the specifications are still the same. It is important that the line voltage and frequency, temperature, humidity, pressure all be very stable. The lead definition and the specific leads and the model of the cardiac vector remain the same. There has been no real change there. Certainly you still want a differential, but a lot of these, like trace visibility, trace width, etc., that's changed quite a bit as we've gone to fully digital displays, as opposed to the old just analog readout. So I would say these specifications, while important, some of them are not quite as relevant as they used to be. Common mode rejection relevant, still, or common mode rejection ratio is still quite useful. Maximum allowed DC current, absolutely important. This basically says that any input lead should have a maximum of 0.1 microamps of DC current. This is for protection. Over voltage recovery time of 8 seconds maximum. Energy reduction, let me go back. Energy reduction by defibrillator shunting. So you have to remember that sometimes patients are being given an ECG when they are in cardiac arrest. And so the measurement equipment needs to be able to withstand cardiac arrest procedures, like the use of a defibrillator, as well as the fact that there may be pacemakers present. So when you have pacemakers present, there are some specifications for how the ECG display should work in the presence of a pacemaker. So all of these specifications, absolutely not something to try to memorize, but they are important because they do, they do say the operating ranges that need to be present for making a clinical measurement. The FDA, as we've discussed in the past, approves equipment. In these cases, the FDA would be doing approval on the equipment that's being used to measure the ECG. You don't need a new approval as long as your equipment is consistent with what's existed in previous devices. So that is why in textbooks published in the mid 2000s, you see, or in the mid 2010s, you see specifications from 1991 is to deviate from an existing piece of equipment can require new FDA approval, and those approvals have become more strict as time has gone on. So, a lot of times, what that means is instrumentation used in clinical applications has obsolete specifications, but they're not changed or updated because the new approval process is so difficult and the testing procedure is so expensive and so stringent that people continue to use the older equipment in the clinical environment.